Swayam Prabha. Digital India. Educated India.
Hello everyone. Now we will start a new topic. It is a hook removal in Drawframe in the advanced form. In the last session we have discussed the basic hook removal theory for leading and trailing hook in the Drawframe, and here we will be discussing little bit in depth, but thing is that we are not going to discuss all the derivations, and here we will discuss the how the hook removal takes place, different types of hook removal takes place, and with their some assumptions, and the content of this session will be leading hook straightening process. There are 4 types of hooks we will be discussing. One is the leading hook straightening process, then trailing hook straightening process, both end hook straightening process, and the straightening process of clamped fibers. So, if the motion is in this direction from left to right, and the leading hook will be, this is called leading hook, and there will be this is trailing hook, and you may have both end hooks and clamped fiber. So, here in this session we will discuss the all 4 types of hooks or clamped fibers. So, simulated sliver consists of different types of fibers. Let us see what are the type of fibers. One is leading hook, then trailing hooks. So, the fibers, the sliver has been simulated, where it consists of leading hook, trailing hook, then it consists of both end hooks. So, there may be both end hooks, okay, and clamped and straight fibers. Clamped fibers are there, and also there will be straight fibers. So, straight fibers will be there. Okay. All fibers are oriented parallel to the direction of drafting. That is actually our assumption. The actual configuration is, this is leading hook, and here in this is the actual configuration, and during simulation what was discussed here, it is actually it is shown as a right side, the leading side thick place, and trailing side thin place. In this way the hooks are being represented. Similarly, for trailing hook, trailing side thick places and leading side thin line, okay. And in both side the thick lines are on both side, and at the center there will be thin line, and in clamped type of hook, at the center it is thick line, and in both the sides there will be thin line, and the straight fibers is shown by the thin line. That means, thin line if it is there, so we do not have to be worried. So, it is a straight portion it depicts, but the thick portion it is a hooked portion. Now, the assumptions roller gauge, the roller gauge is greater than the fiber length, so that the drafting can take place. So, in this derivation, so it is assumed that roller gauge is greater than the fiber length. The most of the fibers are accelerated to the surface speed of the front loader before it is reaching to the front roller nib. So, earlier what we have discussed, the fibers after reaching the, in ideal case, after reaching the front roller nib, then only fibers will take the motion of the front roller. So, this is the, if this is front roller, back roller. So, but here it is assumed that fibers are actually accelerated to the surface speed of front roller before it is reaching to the nib. That means, here this is back roller and you have it is a front roller. Now, this is a fiber. So, there will be a floating fiber. Floating fiber, what we discussed earlier, that it will either take the back roller speed or front roller speed depending on the contact. So, in this discussion, it has been assumed there will be a friction line, okay, that maximum friction line, that if it, when as soon as it reaches the that line, it crosses that line, the fiber starts moving at the speed of the front roller before it is reaching the front roller nib. Now, the fiber movement, floating fibers move at back roller speed until gripped by the front roller nib, or their midpoint reaches the accelerating point, that is maximum friction point. So, there will be an accelerating point. Suppose these are the assumptions, front roller and back roller. So, this is a floating fiber and there will be one accelerating point. So, this fiber is moving at the back roller speed, at slower speed, and when this fiber, in the second instance, when the fiber is just touching the accelerating point, this is the accelerating point. So, still it is moving at the back roller speed, but as soon as the 50% it is crossing the half midpoint, then it will start, even if it is not gripped by the front roller, still it will start moving at the front roller speed. So, there will be an accelerating point, fibers then instantaneously attain the speed of the front roller surface. So, from back roller surface, suddenly fiber will start moving at the front roller speed. So, that as soon as it 50%, half of the fiber crosses the accelerating point. So, it will be immediately, it will take the speed of the front roller. And hook and body motion will be different here. The motion of the hook portion and body portion are independent of each other. So, body can move at a certain speed and hook can move at different speed. Suppose then only the straightening will take place. Like let us consider the leading hook. So, here the body is moving at certain speed, say V1, and hook is moving a certain speed, different speed of V2. So, if V2 is more than V1, then only it will, the hook will get straightened. So, this is assumption body and hook portion are independent, they can move, although they are the part of the same fiber, but they can move independently. Their accelerating point is located at the same position. So, their accelerating point will be at the same position. Now, this is the schematic diagram here. Now, this is the back roller, here it is a front roller. So, back roller speed is V b and front roller speed is V a, and then after drafting there will be outgoing fibers. Okay. Now, pressurization is that, so in the necessary condition for drafting is pressurization that we have already discussed, otherwise there will be the roller slippage. So, we have seen mathematically what will be the impact of top roller pressure on roller slippage. So, the force applied by the roller to grip and draft the fiber. So, there will be force, pressurization will be there top from the top, then it will grip and draft the fiber. And roller gauge is also important. The distance between the front and back drafting roller is the roller gauge. This is the roller gauge, and here we can see. So, this is the roller gauge, front and back roller distance. The speed difference, between the front and back roller, that causes the fiber straightening. So, fiber straightening takes place due to the during the drafting, when there is a speed difference. If the speed, they are moving at same speed, so there will not be any effect on either drafting, stretching or hook removal. You can see here, this is the fiber accelerating point, here is the fiber accelerating point. You can see the from this point, at this point fiber gets accelerated, and then acceleration, it is attaining the speed of the front roller. So, fiber straightness, what is the definition of fiber straightness? So, the fiber straightness is expressed by this eta and describe the number of hooks. So, it is defined as the effective fiber length, that is the effective fiber length is C b, this is the effective fiber length, C dash b dash is the effective fiber length to the original length without hooks, that is d a. So, without hooks d dash a dash. So, if we straighten, so that the ratio will be the straightness. So, C dash b dash by a dash d dash, which is less than 1, and when it is straight, for straight fiber it will be 1. So, maximum fiber straightness is 1, completely straight fiber, and hook characteristics, most fibers are in the most fiber, the hook portion length is smaller than the body portion. So, that is our assumption here. This is the body, hook is not considered to be like this. Okay. we assume that hook portion is smaller than the body portion, that is assumption. Based on the assumption 3 and 4, fiber movement and hook and body motion respectively, there is a time difference between the midpoint of the hook portion and the body part arriving at the fiber accelerating point. So, there will be difference because this is the roller, front roller, back roller. So, if it is a accelerating point, so midpoint of the hook part. So, if we see this is the hook part. So, this here it is a midpoint of the hook part, the fiber is reached and the body part. So, body part, this there will be time lag. So, when the body part will reach the midpoint will reach midpoint of the hook, the body part is behind that. Okay. The time difference facilitates hook removal. So, because at this point the hook portion will have higher speed. So, body portion will be moving at the back roller speed. So, this time difference is actually responsible for hook removal. That is actual, that is the basic assumption. Fiber straightness in drafting process, two categories of straightening process is there. So, one is that not affected by the, it is not affected by the front roller speed. So, front it is the hook straightening will not get affected by the front roller and affected by front roller. So, there will be two types of straightening process. Some hooks may be straightened early before reaching the front roller. So, during this time, so let us discuss here. So, during travel, so this hook will be removed. Other hooks are harder to remove and may be straightened only when the fibers gripped by the fibers which is moving at the other front roller speed and straightened it fully. So, that there will be two types of hooks. So, the parameters which we will be using for analysis here, the total length of hooked fiber is L. So, input fibers straightness is eta and output fiber straightness, front roller velocity is V A, back roller velocity V B, draft ratio E, distance between the front roller nib and fiber characteristics R, capital R. So, this based on these assumptions, now we will start discussing the hook removal. So, as we have discussed, we will discuss the hook removal process in 4 stages. First, let us discuss the hook removal of leading hooks. This is the leading hook. Now, here the leading hook straightening process is in a leading hook, the hook portion changes velocity before the body portion. So, that is what we have discussed. This is the body, here is the body portion and here is the hook portion. The hook portion will accelerate before the body gets accelerated. So, that is the change in velocity, means it velocity increases. Now, from this representation, the original length of hook and body portion are L1 and L2. So, this is L1 here and L2 is the body portion. This is the body portion. So, this one is hook L1 and L1 and here it will be L2 body portion. So, L1 plus L2 will be the fiber length. Straightening process in which is not affected by the front roller in this case. So, what we are discussing, we told that there will be two situations. One is the straightening process which is not affected by the front roller, another is it is affected by front roller. So, when we are discussing which is not affected by the front roller, in these cases R is the distance between the front roller and the fiber accelerating point. So, this is fiber accelerating point. Here actually hook portion, the leading hook portion is actually straightened before it reaches the front roller. This is large enough for straightening occur. So, this distance is large enough. Okay. At that condition, if R is very high, so R is very high, so that it will take some time to reach the front roller nip and there is a gap. So, in that case the straightening process is not affected by the front roller. Now, case A, this diagram is showing the case A, though that is a fiber straightening process. In case A, this is the diagram here, 4 points are there of leading hook exist in the drafting zone. So, T1 to T4, T1 this is T1, T2, T3 and T4. There are 4 points are there during the in the drafting zone. So, T1, what is T1? This T1 is that the entire fibers held back by the back roller and move at the back roller speed. So, this fiber, total fiber is gripped by the back roller and it is moving at the speed of the back roller. Now, T2, what is T2? T2 in the straightening process starts. So, at this point the straightening process will start because the hook portion, midpoint of the hook portion has reached the accelerating point C. So, midpoint of the hook portion, that is L1 reaches the accelerating point and the hook part accelerated at the front roller speed, while the body part is moving at the back roller speed. The speed difference or relative movement causes the hook to straighten. Now, coming to the T3, the midpoint. So, here at this point the straightening will take place. So, most of the straightening has taken place. The midpoint of the body, now the midpoint of the body at T3 point, it reaches the fiber accelerating point, then whole fiber body and hook portion will move at the front roller speed, because it has its body portion's midpoint has reached. The hook portion straightened only until the midpoint of the body reaches the accelerating point. So, during this point, this from T2 to T3, the hook removal takes place. So, that means the longer this distance, better will be the leading hook removal. Now, T4 is that where the straightening process ends. After beyond that, the straightening process will not happen. So, main straightening is taking place between T2 and T3. The entire fiber will move at the front roller speed and the movement will be uniform. So, even if there is any hook, so that hook will not get removed at T4. From the figure we get, so this is we can derive, we are not going to derive all these equations, but we will try to discuss this equation. L3 we can calculate, okay, L3 eta L 1 minus eta by 2 multiplied by L. Okay. What is L3? L3 is the body part at T2 point. So, this eta L is the straightened part, that is effective length, and 1 minus eta into L is gives the hook portion. So, if that eta is the fiber straightening point, 1 minus eta is the fiber straightness. So, L4 we can calculate. So, what this L4 after straightening we can calculate. So, L4 equal to eta L plus V A minus V B by 2 into T by 2, and V A minus V B by 2 is the average velocity change. So, velocity change is there. So, that what is the average velocity change? So, multiplied by T. So, that is the displacement. If we multiply by T, T is the time to change. So, here L3 is the distance between the trailing end of the hook. So, L3 is the distance between the trailing end of the body and the accelerating point, okay, at T2, that is L3, and L4 is the trailing end, distance of the trailing end of the body at and accelerating point at T3, okay, and T is the time for relative movement between hook and body portion, that there will be some relative movement will be there. So, L3 minus L4 equal to V B multiplied by T. So, only considering the body part here which moves at the speed of the back roller V B. So, the displacement L3 minus L4 equal to speed into time. So, V B multiplied by T. From equation 1 to 3, what we get? We get, after replacing, we can get T is equal to 2 L multiplied by 2 eta minus 1 divided by V A plus 3 V B. Okay. So, after replacing, so from equation 1 to 3 we can get time in terms of velocity, fiber length and the fiber straightening. Okay. So, input fiber straightness, and L is the total length of fiber. The input fiber straightness, okay, we have seen eta, and the output fiber straightness after the straightening point okay, after drafting, that also we can obtain. So, the output fiber straightness multiplied by L equal to input fiber straightness L plus V A minus V B by 2 T. This is average velocity change. Eta dash T L is the effective length or straightness portion after acceleration, that is after acceleration, that is the effective length. Eta L is the initial effective length. So, this will be more, here this will be more because it is straightened, and so this is after straightness, after drafting portion. Here eta L will be the before drafting portion, and V A minus V B by 2 multiplied by T, this will give the additional fiber length gained at time A. Okay. T is the time for which relative movement happens between hook and body. Total length of fiber, input fiber straightness, and V A B V are the front and back roller speed. Now, case B and C, let us see case hooks are fully straightened during drafting. So, earlier it was the case was different, here the two cases are there where during drafting the whole leading hooks are straightened completely. So, difference between these cases are case B, fiber moves, fiber becomes fast when the front end is nipped by the front roller, and here you can see the this fiber here when the front end is nipped by the front roller. So, here although this is straightening is taking place, but fiber the body part will start moving at the front roller speed when the leading end reaches the front roller nip. So, as from this picture we can say, although at T2 time the straightening takes place because the midpoint of the hook has reached the accelerating point, but the body midpoint has not reached. So, body portion is moving at the front back roller speed, but as after this the fiber is reached at the front roller nip, that leading end, then only the body is body also does not, midpoint of the body is also behind the accelerating point. So, the movement is mainly due to the roller grip, front roller grip, as front roller at the fiber leading end has reached there. Now, case C, what is that? Fibers become fast when the midpoint of the fibers reach the accelerating point. That means, here the fiber whole fiber is moving at the speed of the front roller before the midpoint reaches the accelerating point. So, that is why the fiber moves at the front roller speed after reaching, after the leading end is gripped by the front roller, but case C is that before that, before the mid tip fiber leading end is gripped by the front roller, the fiber starts moving at the front roller speed. It will move at fast because the body midpoint of the fiber body reaches the accelerating point. Now, we can see here. Now, here the fibers straightened here, and at T3 the midpoint of the fiber has reached the accelerating point. So, this T3 at T3 the fiber starts moving at the front roller speed, okay. And similarly at T4 will be there. From T3 it will start moving at the front roller speed, but here at T2 it is not moving, although the straightening takes place. In case of case B. So, the output fiber straightness in this case is 1. So, output fibers will be straightened. So, that straightness will be 1. So, output fiber straightness we can derive. So, this is the relationship. So, output fiber straightness will be 3 multiplied by input fiber straightness minus 1 minus 4 2 eta minus 1 by E plus 3. This relationship was derived by long calculations, and there are many assumptions are there, simple assumptions. So, this portion first 3 eta minus 1 represents an initial estimate of fiber straightness after drafting. This is the, and but not all the fibers are straightened equally, and some fibers still retain the slight hook portion due to incomplete straightening. The correction factor below removes the overestimation. So, this is the correction factor for adjustment. So, here is the second part is the correction factor. So, which will reduce the straightening, because all the fibers are not getting straightened. So, the eta value, eta dash value, output fiber straightness should not be very high. So, just to take care of this, this is the correction factor which is reducing the overall estimate. Now, here E is the draft ratio, E is the correction factor, here this is the correction factor. More correction is needed because draft could not straighten the fibers as effectively. So, as the draft ratio reduces, so correction factor will be more. So, if this is the draft, if it reduces, the correction factor will be more. So, because the at lower draft correction factor, the straightening will be less. So, we need higher correction factor. Time taken for the fiber to straighten can be calculated. This is the time taken. So, this is the length of the hook portion. L1 is the so, L1 is the length of the hook portion, and here is the average velocity. So, L1 by average velocity is the time taken. So, length of the hook portion divided by average velocity. What is average velocity? V A minus V B by 2. Okay. So, V average, so L 1 by V average is the time taken, okay, which is shown here. Output fiber straightness is as follow. This is the output fiber straightness that we have discussed earlier. So, here the certain numerical factors, that 2, 3, 4 in the above equation appears in the fiber straightening equation. This value could be derived from the empirical relationship. So, these values are actually derived from the empirical relationship observed in fiber drafting and straightening experiments. So, through experiments we can get this value approximate. These are approximate values. They account for how different fiber segments contribute to the overall straightening process, okay, including the effects like symmetrical hook removal, drafting acceleration phase and fiber elongation. So, these are the assumptions. So, these factors we get from the empirical relationship by experiment. Straightening process is affected by the front roller, the case D. Now, earlier we discussed that without the front roller. Now, case D is the hook removal occurs, which is affected by the front roller. Straightening starts when the midpoint of the hook part reaches the fiber acceleration point. That is true for earlier case also. Straightening ends when the fiber fore end, leading end of the fiber is held by the front roller. Time for straightening, this is the time which has been calculated, 2 r minus L multiplied by 1 minus eta by V A by V B. This is V B is the back roller speed and this is the front roller speed. V A is the front roller speed. R is the total space available for straightening. L, this part L multiplied by 1 minus eta is the length of the hooked portion, and effective straightening distance R minus L multiplied by 1 minus eta. So, this difference is the effective straightening distance, and here is the V A by V B, V A plus V B by 2, this will be average speed. So, V A plus V B by 2, this is the denominator is not showing. So, V A by V B by 2, V A plus V B by 2 is the average speed. So, here we can see from this diagram, we can see here the straightening process is affected by the hook portion. So, or the front roller. So, output fiber straightness after drafting is given by this relationship here. Now, where this first portion of this relationship 3 eta minus 1 is the optimum baseline fiber straightness before the influence of the front roller. This is the before the influence of the front roller, and here E minus 1 is the drafting effect, R multiplied by E minus 1, this is the additional straightening effect due to the front roller influence, and L multiplied by E minus 1 is, it could be normalized factor, and 1 minus eta is the, it is included because straightening process not only depend on the roller influence, but also on fiber initial stage. So, now case E, where we the consideration is that there is no hook removal for leading wood. So, where hook is not being removed. So, this is the condition. Here what happened, we will see that at this point the hook portion is reached the front roller nib with the hook before removal, where the R distance, that is the accelerating point distance, is very close to the nib of the front roller. At that point, so it will immediately the fiber hook will reach the front roller nib and hook will not be straightened properly. So, R is less than half of the hook length, that is too small R. So, in that case immediately fiber is entering, hook is entering. So, before the midpoint of the hook reaches its accelerating point, the fore end of the fiber, that is fore end means this is the fore end. If you see this, we can say it is not leading end, it is a fore end of the fiber is held by the front roller nib. So, at that condition, so midpoint of the hook has not reached, that means the hook is not getting the speed of the front roller, but before it reaches the fiber hook is gripped by the front roller. So, there is no chance of the leading head to be removed. So, R for very small r, hook cannot be straightened. So, output fiber straightness will be eta dash equal to eta. So, there is no hook removal. So, both the input and output fiber hook straightness will be same. Now, we will discuss the trailing hook straightening process. In this case, the body portion changes the speed before the hook portion. So, now you have, here is the hook. So, let me draw in other color. This is the hooked fiber, and here to remove the trailing hook, the body portion, this is the body portion, has to move faster than the hook portion. So, body portion should reach the accelerating point, midpoint of the body portion should reach the accelerating point earlier than the midpoint of the hook portion. Now, this is the situation here. Now, we can see the straightening process not affected by the front roller. So, here straightening process is not affected by the front roller. Now, condition is R is more than L2 by 2, that here R is L2 by more than L2 by 2, that means the what is L2? L2 is the body portion, midpoint of the body portion. So, here the straightening process starts when the midpoint of the body portion L2 reaches the accelerating point. So, here we can see this is the L2. Now, at this point T2, at the point T2, the midpoint of the body has reached the accelerating point before the hook is reached, and it moves at the speed of the front roller. Now, here case A is that the straightening starts where when the midpoint of the body L2 reaches the accelerating point. This is the case A, see here, and straightening ends when the midpoint of the hook reaches the accelerating point. When the midpoint of the hook L1 arrives at the fiber accelerating point. That means, when as soon as the midpoint of the hook is reaching at the accelerating point, that means both hook and body will move at the same speed. So, there will not be any straightening further as this point. So, at this point the entire fiber moves at the surface speed of the front roller. So, that is clear. So, time for straightening will be, we can derive the time for straightening here 2L multiplied by 2 eta minus 1 divided by V A plus 3 V B. So, that is can be derived here. This is exactly the same as the leading hook equation 4, and the leading hook portion where the hook portion changes speed fast, while the trailing hook portion, the body portion changes the fast. So, here in this trailing hook case, the body portion changes the speed fast here. Despite the difference in order to accelerate, okay, the hooked portion of both cases need to be straightened by same effective length, and the force remain same for both cases. Okay. Now, output fiber straightening after drafting. So, we can use this equation, this equation can be derived here, and eta is the initial straightness, and this additional. So, this additional straightness is due to drafting, which depend on the draft ratio. Higher the draft means more stretching, this is the initial straightness. So, now case B, it is complete straightening in drafting zone. So, initial that this case B is where within the drafting zone the straightening takes place. The trailing hook is straightened completely during the drafting portion. That means, it is within the floating fiber zone, it gets straightened before it reaches the front roller nip. Now, you can see here, this is T1. At T2, what happened? T2, the midpoint of the body has reached, okay, whereas the trailing portion, that is the hook portion is behind that, which is moving at the speed of the back roller. But the thing is that here the R distance between the front roller nip and the front roller nip B and the accelerating point C is high. So, before it reaches the front roller nip, so there is a movement. So, that there is a space, but that means it will take some time to reach the front roller movement to actually the time before the nip of the before the midpoint of the hook reaches the accelerating point. So, that time is high, so that it will get straightened completely. Okay. The entire fibers move with the front roller speed, that is not it is for front roller speed, that is the body part of the fibers will move at the front roller speed. Time for straightening, so T equal to 2L by, so that means L1 by VA minus VB average speed divided by 2, that is the time for straightening. So, output fiber straightness is eta dash, which is 1 maximum, the complete straightening is there. Straightening process affected by the front roller nib. When R is less than L2 by 2, that means the midpoint. So, here you can see the midpoint is reached, but R is less than L2 by 2, that means before the midpoint of the body part arrives at the fiber accelerating point, the head, the leading end of the fiber is nipped by the front roller. Thus, straightening process starts ahead of time. So, here this midpoint has not reached, but this will be gripped. So, straightening process will start ahead of time, and in case 3 the straightening start earlier, because the head of the fiber is nipped by the front roller before the midpoint of the body part reaches the accelerating point. So, that is the condition. So, if R is less, so this tip is reaching the head part, the leading part of the body part is reaching at the front roller nib before the midpoint reaches. So, it will start moving at the speed of the front roller by the grip of the front roller, but not due to the accelerating point. So, it starts earlier. The straightening ends when the midpoint of the hook. So, as soon as the midpoint of the hook reaches the accelerating point, that means the both hook portion and the body part will move at the same time. So, if we have longer time between this, then the straightening will take place, complete straightening will take place. Time for straightening, if we can increase. So, T equal to this equation can be derived. So, 2 multiplied by L multiplied by 3 eta minus 1 minus 2 R. So, V A plus 3 V B. So, that is the time it can be derived. So, this part at the top, the numerator represents the net fiber length that needs to be straightened. This can be derived considering the initial straightness and roller influence, and the denominator V A plus 3 V V represents the effective velocity difference, determining how quickly the straightening process occurs. So, output fiber straightness also we can derive. This is the output fiber straightness. So, this is output fiber straightness eta dash, and the input fiber straightness plus this total factor, which can be derived, which is a function of the draft total length of the fiber, initial straightness, okay, and R, distance from the accelerating point to the roller nib. So, all these factors are there, and this can be derived. So, eta represent the straightening contribution, and this total factor represents the additional straightening effect due to drafting. So, this equation can be derived based on some empirical relationship. Now, case D, where straightening ends. So, further straightening does not take place when the head of the hooked fiber is held by the front roller. That means, where the hooked portion is held by the front roller, the fiber then moves at the speed of the front roller, and time for straightening, this can be derived here. Now, here you can see the fibers are, this is the fiber here. Now, at this point T4, the straightening ends when the head of the hooked part is held by the front roller. Total straightening time depends on how much the fiber needs straightening, okay. That is a numerator, and that is how much fiber needs the straightening divided by the how fast the back roller is pulled. So, that is V B. So, that means the we are talking about the trailing hook removal. So, the fibers, that hook portion should be pulled by the back roller. So, higher initial straightening, more hooked fiber, that straightness means more time is needed for straightening. So, we can see here more time will be needed, and higher the back roller speed reduces the straightening time. And the output fiber straightness becomes this equation, where eta the output fiber straightness equal to input fiber straightness plus E minus 1 draft minus 1 multiplied by 2 eta minus 1 by 2. So, this relationship can be derived, where this factor, the here this factor is the correction term, where E minus 1 represents the degree of straightening beyond the original fiber length. Higher the draft means more straightening force, and 2 eta minus 1 represents the initial waviness of the fiber. So, that this is initial straightness. So, if we know this factor, we can calculate the output fiber straightness. The whole equation is divided by 2 to account for the fact that not all extra stretch directly convert into straightness. So, we are trying to average out, some part of the stretch is distributed, and the straightening effect is only partially realized. And the case E, which is the last case, the trailing hook is completely straightened in the drafting process. During the drafting, like leading hook, here the condition case E is the trailing hook is completely removed. This is the case here. Now, you can see in this case the head of the body is reached before the hook is entering into the this accelerating point, and the distance between the midpoint of the hook and the accelerating point is more than the distance between the midpoint nip point of the front roller and the accelerating point. So, the fibers body part will be pulled, and there will be, it will take some time, sufficient time to fiber getting straightened. So, output fiber straightness we can have 1 if it maximum straightness 1, and time for the hook removal, we are getting time for the hook removal L 1 by V 1 minus V 2 by 2. So, from there we can see the in the trailing hook portion also there is a chance for all the fibers getting straightened. Now, between the leading hook and trailing hook we have discussed many possibilities. So, it is not that only one possibility take place, one case take place. So, all the cases are there actually they can happen depending we can there will be some dominant case where by setting the change we can increase that effect of that case. So, it is not that all the fibers are getting straightened. So, all the leading hook are getting straightened, there will be in between, but as the distributions this diagrams are ideal case. So, distribution will be there. So, it can happen any all the combinations will be there in the after the hook removal at the drafting it will be present at the sliver of the drafted sliver, okay, output sliver. So, we will stop here. In the next session we will start other aspects like both side hook will start, okay. Till then, thank you.